Alrighty then. Hello and welcome to another happy super fun time with graph theory and friends, computer science 2DM3. Just a little bit of some update. Last time, some people liked this idea of having these English interpretations of formulae. You didn't just want to see symbols, you wanted to see what they mean, whatever that means. So symbols can always mean different things to different people, but in order to provide you with more meanings, I've updated the abridged lecture notes with a new section on relations and what they mean, as it were. So for example, if we're talking about equivalence relations, an equivalence relation models similarity, and then transitivity means things similar to things that are similar are themselves similar. Okay, and I tried to go back to the slides from last week and try to give you what was already on the slides, but more with intuition. For example, here is just a few intuition on domain and range and what they mean, right? So the domain is the dots that have an arrow going out of them, right? And you can, here's a boring formula, but then here's some, intuitively obvious interpretations. If you take a graph R and you flip all the arrows and you say, hey, what are the arrows that come out? Well, you flip them all. So that's the same thing as the arrows that go in, right? So intuitively. Try to see if you can convince yourself of these intuitively, and maybe that will help you with the formal proofs. There's, of course, like a billion properties. Maybe I'll add a few more. I just didn't want it to be too daunting. I thought the slides did a sufficient job of being too daunting and the homeworks. So I thought maybe keep this abridged lecture notes, easy breezy, lemon squeezy. Yeah, as easy. Alrighty then. And of course, to continue with our idea of still going a bit forward, but not too fast, and still going back, we'll continue talking about graphs as relations and reachability and closures. So we're really staying here. We'll try our best to stay here or close to here for the rest of the term, especially since graphs are so important to computing and science. Okay, so we'll look at that. Are there any questions or concerns before we begin? As usual, I have the chat beside me, and I'll open an auxiliary one just in case I miss things from that one. How much is the bonus assignment worth? I thought that was posted on Avenue, so please check there. If not, we'll have to revisit that discussion. Okay, thanks. So last time we were talking about multisets and bags and the pigeonhole principle, and then we made it a little bit to graphs, and then we were short on time. So just can I see like a show of hands or likes or whatever? Who would like me to review multi-bags? Who would like me to review everything in the first bullet point? Maybe I can do it quickly, but I'm just curious. Or is this sufficiently okay that you don't want me to review it? So let's see. Please vote. Vote now. All right. Okay. I'm sorry. Not show of raised hands. I meant in the chat. Can someone just add a bunch of likes? There's over 150 people, and my screen only shows like 9. So please like that review comment if you would like to do the review. Okay. All right. So we have enough reviews, which apparently go up and down. I didn't know that was okay. All right, so we'll do the quick review. We'll do the quick review of what these things are. Okay. So a bag, right? Also sometimes called a multiset. It's like you have a bag, like an actual sack, from the dollar store, and you throw a bunch of stuff in there. Okay. The stuff in your backpack is gonna, move everywhere. It's gonna, jumble around. But the number of pencils you have in there matters, right? The number of napkins you have matters. The number of chocolate bars matters. So the order doesn't matter. You know, if they get shuffled around, that's okay. But how many chocolate bars you have actually matters. Okay. In a set, you have a class of chocolate bars. I don't really care how many. Do you have a chocolate bar? Yes or no? Okay. So sets are all about yes or no. They just want to know if it's there or not. Does it exist? Bags are, I need to know how many, right? It's not enough that you went to the store and bought a chocolate and bought some chocolate. I need to know how many chocolates did you buy, right? If you go to your parents and say, hey, I bought some chocolate, they might be like, how many chocolate did you buy? I'm curious how many, okay? And so this means we replace the membership symbol. We're not using, membership isn't the primary thing, but rather count. We count how many times something occurs. So two bags are the same precisely when every element X occurs the same number of times in each bag, okay? If I take my Halloween candy bag and your Halloween candy bag and I fuse them together into one big candy bag, how many candy is going to be there? Well, for each kind of candy, it's going to be the amount in my bag plus the amount in your bag. Okay, so the operations now, instead of being a union or and, now they become arithmetic operations. Okay, so we're getting closer back to that tropical mathematics. Okay, so let me just pull that up real quick, just in case. I feel like occasionally I say some words and maybe some people are not comfortable. So here's a review of some tropical mathematics, chapter 15, assignment 2. Okay. Alrighty. So the order doesn't matter. You can shuffle them around, right? So 41014, you can change the order, but you can't drop multiplicity, right? How many times it occurs does matter. Okay. So that's what it is. Okay, ducks. This is I would like to suggest to some of you to look at this. So this is possible for sets. A set S is all the things X that happen to be in the set. But a bag, ooh, is this even possible? You can consider all X that happen to be in the bag. I need to know how many times they occur in the bag. All right, to reconstruct the bag, I need to know how many times. So this, not so easy. Hint, unions of bags. So try to do this, ask questions on course help, and maybe we'll give you the answer. Unions of unions is the answer there. Okay. So that's what's going on there with bags. The pigeonhole principle, right, says if you have a bunch of pigeons and you want to stuff them in a bunch of holes, if you have more pigeons than holes, then obviously some hole will have multiple pigeons. Okay. I have seen some people teaching combinatorics refer to this as the common sense principle. Okay. The idea of pigeons and holes is a bit, it's nice to explain. It's a bit tricky to use with formulae. So we, in our book, LADM, Logical Approach to Discrete Math, we use it this way. We say, so this is why we talked about bags, right? We say if you have a bag of numbers, then the average of the bag is at most the maximum. And this seems intuitively true, right? You know, the average is at most the max, right? So this seems reasonable. What is the average really? So the average is the number, right? That if all your quantities had that number, then you would get the same total. Okay, so you have a bunch of things and you're going to sum them up, right? And then you say, what if all those things had the exact same value? I want to get the total, the same total. What value would it be? And that value is known as the average. Okay, so it's intuitively you expect the average to be at most the max, and the pigeonhole principle says, yeah, this intuition is true, right? Because the average is supposed to be the thing that lands in the middle, and if it lands in the middle, it's got to be less than or equal to the maximum. Right? So I hope that's clear. The book has a nice discussion on why we don't do it this way. Dijkstra has some notes online. If you visit the EWD archive, you can read more about this. So that's a cute little principle. And here's an application we saw last time. If you have people in a room, there's 8 people, and there's only 7 days of the week. And then, of course, some 2 people must share the same birth date. Otherwise, there's going to be a mismatch. When we talked about it last week, we said, hey, consider people in Toronto. Toronto has over 1 million people. The average human head can have only about 500,000 hairs. So some people, if you give each person a number of their hairs, the maximum number is 500,000, but there's over 1 million people. So some number of people are going to have the same number. So they're going to have the same number of hairs. This argument, in order to continue with these intuitive things, I've tried to give you this argument again down here somewhere, right here, right? So then at least something must be visited twice, right? So you'll see it again here in an informal setting. So the point of these notes now is to try to point you into intuition and try to get you more comfortable. Okie dokes. And please let me know if that doesn't work and if you need more help. All right. So is everyone okay with bags and pigeonholes? Can we move on to closures? So let's check. Who's good to move on? Can somebody say move on and we'll have a bunch of likes?
One.
Okay. All right. So one person, but let's see if there's more likes for that that Tammy gave us, just to make sure we're good. All right. Don't want to leave anyone behind. Okay. So here's a closure. Here's a closure. To avoid giving you multiple definitions, you are welcome to. So the slides have been posted, but here is a generic definition that maybe will be helpful. Okay. So suppose you have a bunch of things and they're ordered, right? Less than or equal to, divisibility, implication, subset inclusion, relation inclusion, and you just have some ordering. And phi is a property. And you say, hey, sometimes I have things that don't have the property phi. Can I add to them, or can I find something a bit bigger, or something that contains my element but satisfies it? And if you can, right, that's called the Phi closure, right? So you say Q bar is the Phi closure of Q precisely when it's the smallest member that includes Q and satisfies phi, right? So you're saying, oh gosh, the number 3.14 is not an integer. If only I could find an integer that is at least as big as 3.14, and it's an integer. So if only I could find a number that is at least 3.14 and is an integer. Well, that number is 4. 4 is the largest integer greater than 3.14. Right, it's the largest number that has this property. Okay. Sorry, it's the smallest number with this property. Apologies. So this is called the ceiling function. The ceiling function says, let's find the smallest number that includes our number and is an integer. Right. So you've seen these closures before, not terribly new. Right. And the idea is the closure is a solution to the problem. It contains the original part, and it's the smallest solution. So if P is another solution, and P contains it, then P has to contain the smallest possible solution. So you've seen these characterizations before. Okay. So let's go back here. So here's an example we talked about last time. We said, hey, when you're working with a graph, your graph might not be symmetric. And so what you're doing is you throw enough elements to make it symmetric, right? So it's not symmetric. We throw in enough elements to make it symmetric. Just curious, does anyone want to see a proof? Or an informal proof? All right. Okay, so here's an informal proof for the. So we're saying we want R. We want the symmetric closure of R. Okay, but the symmetric closure of R is going to be something that itself is symmetric, right? So S is the symmetric closure of R, right? Means that S is contained in S converse, and it contains R, and it is least with these properties. Okay, all right. But then you'll notice this part right here tells us that S is the same thing as S union S converse. Remember, inclusions can always be phrased in terms of unions. So the first part is the same as this. So now we have a recurrent relationship for S. Okay, and down here, the second part, this tells us that S is the same as R union S. Okay, and this last part as well. So it looks like we have a definition for S. S has to be this, and S has to be that. And so by some formal shenanigans, all right, that I'll just omit for a little while, just to make this easy, we find that S is actually going to be just R union R converse. Okay. All right. So this is what we find. Not too difficult. All right. You replace this S by R union S, substitution in Leibniz, right? And then you use the rule again, and then you can discharge that part as well. Okay. Pseudo proof, yes. Pseudo proof. But here's another proof. Here's another one. So what does it mean to be symmetric? It means that for every arrow going one way in your graph, there's an arrow going in the opposite direction, right? So R is symmetric means that R is contained in R converse, right? But this is the same thing as saying R is equal to R union R converse, right? Right? So you can phrase it like this. But this is the same thing as saying R is equal to R converse slash union R. Okay. So if your relation is already symmetric, then this property will be true. It has itself, and it has all the other flipped arrows. So to take something that's not symmetric, you just add in the flip. Okay. So lots of pseudo proofs. So here's a question. Is this a symmetric graph? Does anybody know? Vote now. Vote quick. Exactly. It's not a symmetric graph because here's an arrow from 3 to 0, but there's no arrow the other way around. Okay. So a symmetric graph has a lot of useless arrows going in both directions. And so normally you just don't draw the arrow part, right? There's 2 here, 2 here, 2 here, and 2 here. So symmetric graphs usually are drawn without the arrows. Otherwise, it looks like a mess. All right. Likewise, reflexive means it has loops. So is this one a reflexive graph? All right. Reflexive means there's a loop at every node. Is this a reflexive graph? Nope. Good. Just trying to get you guys to be comfortable with these things, right? Here's one loop. Here's another loop, but I'm missing one here, here, and here. I'm missing 3 loops. So this is not a reflexive graph. All right. So to make it reflexive, I just throw in all the loops, right? It's missing a loop here, here, and here. So to make it reflexive, I just throw in the loops. That's it. I don't do anything else. So closure says throw just enough in there. Okay, so closures are all about add just enough so that the property will hold. Okay, we don't add too much, just enough. So for example, you might have seen the word closure before when you talk about circles in first-year calculus. You say, hey, consider all the points whose absolute length is less than 1. Okay, it's less than 1. That means you're talking about the unit circle, but without the boundary. You said less than 1, right? So all the points that their absolute value is less than 1, means their distance from the center 0, 0 is less than 1, and so they never touch the boundary. All right. Now to make this a closed circle, the closed unit circle, we throw in the boundary. All right, and now you'll have all the points that are at most 1. And if you don't like calculus, you're welcome to ignore what I just said. That's okay too. All right. So now we're going to get to the really interesting one. So these ones are really easy. They have a descriptive. They have a constructive definition. This is how you make it. This is how you make it. Right. But in general, closures only have these kind of descriptive characterizations. Right. They're only a description. They're an infimum. They're the smallest thing with this kind of definition. So sometimes there is no definition for them. And in particular, this is where we get to the transitive closure. And the transitive is really useful in computer science. It's so very useful. So the other two are just to motivate the discussion here. So remember we said you can think of a relation as a single step in your graph. So here's a step from 0 to 1, right? So I can take one step, that's R. If you compose with itself, that's one step right here, another step right here. So I can take 2 steps from 1 to get to 4, okay? So in general, we write these powers to mean R to the power of n is take n steps, all right? So this is a path. You walk along with n many steps, all right? So taking 0 steps means you can only stay where you are, that's loops. Taking 1 step, that's the graph, the original graph, okay? 2 steps means I can go somewhere else, I can make a loop. Okay, so and they get a bit more complicated as you keep going, right? In particular, notice R star is supposed to be all possible steps, but in a finite graph, at one point there's not, you've walked the path and that's it. You have to keep walking another step, right? And I've tried to give you this intuitive argument right here, right? About when R star becomes a finite union, okay? But the idea is R to the power of n is taking n many steps. If you can only take a path of a certain length, then that's it. There's not much more you can do. There's only 4 nodes, and so at one point, if I have a path with 5 nodes, that means I visited X, I visited Y, U, and Z. I probably visited all these 4, and now I have a 5th one I visited. It has to be one of these, so that means my path actually took me back. All right, so at one point you'll just have redundant paths for finite graphs. For infinite graphs, not as such. So transitive closure means how do I make my graph transitive? I have to throw in all possible steps. So if this is the original graph R, I have to throw in all the loops, R0 to make it reflexive, right? And then I have to throw in all the original ones. Then I have to throw in all combinations of these guys and those guys to get over here. Then I have to throw in all combinations of the previous 2, and then I keep going, right, until there's no, and that's right here, okay? So the transitive closure is really neat because it captures this idea of paths and reachability. If you try to say 2 nodes are reachable from each other, I have a path from X to Y, using R star is really easy, just X, R star, Y. If you don't have access to transitivity and you're not talking about it, maybe because you're not familiar with it and you don't know it, next term or in the future, transitivity becomes a really ugly property, reachability. To say X is reachable from Y, you have to say, oh, there exists a number of sequences. How many? I don't know, there exists a number n, and there exist sequences, and those sequences are, the length is equal to n, and the sequences start at X, and the sequences end at Y, and it's just a mouthful. And I try to show it to you somewhere because it's so very ugly. I thought I had it here, sorry. F path. Right here. So to talk about it without using R star, it becomes a bit ugly, right? There's a sequence of n many nodes where the sequence starts at X and the sequence ends at Y, and every 2 elements in the sequence are related. Like this is such a mouthful. All right, this is very, very ugly. And this is the stuff we're trying to get rid of by using relational operators. Right? When you just have access to R star, you just say X is related to Y star instead of this complicated mess. Right? Here you have to know about sequences. This is fin n. You have to do indexing. You have to look at the endpoint. You have to look at the start. It's very low level. And so that's what we're trying to do with relations, to avoid talking about low level stuff. Okay. So in your programming classes, you might come up, you'll probably see something called Warshaw's algorithm. So maybe 2SO3 or most likely in your second or third year, I think 2GA3 next term, right, on algorithms. So you'll probably see the algorithm to compute the transitive closure of a graph. In particular, if your graph models like people, and every line is like a road between the cities that the people live in, you want to know, hey, can I get to your city? There might not be a direct edge between me and you, but maybe there's a number of edges I can take to get to you, right? And so the reflexive transitive closure will tell you, it will compute that possibility and then just add in a new edge directly from me to you. It will just add in a new one, which represents the composition of me going through all these smaller roads to get to you. Okay, so are we all back? Seems we cut out. Does somebody want to say some words just to make sure we're all here?
We're all good.
All right. So let's look at this graph, right? So here's Ezekiah lives in this town, and Dundurn lives down here, and Dundurn can get to Ezekiah really quickly, right? But maybe Dundurn wants to visit V over here, right? There's no way for Dundurn to get to V, but Dundurn can go to Ezekiah first, then they can go to V, right? So there's a two-step path, and because there's a two-step path, that means VU is reachable from DU, okay? And the reflexive transitive closure will add in a new fictitious arrow, right? It will essentially just add in a new arrow that goes right here, and then all the way right here, okay? It will just add in a new arrow, and then we don't have to do the process of going here, then going here. We just have a direct route, okay? And the fictitious arrow is just to tell us this is reachable. We know that it exists. Okay. In advanced graph theory classes, you'll actually want to do things with this reachability, like how much does it cost? How much time will it be? What's the most efficient? Okay. So we won't try to bring that in, but these things are associated with it, and you might see them in Corman's algorithms book. Okay. So we talked about source and sink last time. And so this time for reachability, N1 is reachable to N2 in 3 steps. Okay, so we take our relation, raise it to the power of 3, and it means N1 goes via E to some place, then to some other place, okay, and then it gets to N2. Okay, so I have to take 3 steps. Okay, so I'm at N1. I travel E and I get to some other place. Then I travel E and I get to some other place. And then I take one final step and I make it to N2. Okay. So these fat semicolons, you can think of them as the intermediary anonymous places I have to visit along the way before I get to N2. Okay. Then the star, the reflexive transitive, just says I can get from X to Y in some number of steps. It might be 3. It might be 0, it might be 105. It just says I can do it in some number of steps, all right? Which is useful to know. So let's look at another problem. Okay, let's. Does anybody want to try to read this in English? All right, so give you a moment to type in. Right, try to read it. All right, like so many of these formulae can be read, and I know that some people have trouble with this. So a good opportunity now. Try to read this formula, please. Okay, so let's please put your reading in the text chat, and we'll discuss it there. You can do it. Give you another 30 seconds. Okay, so let's read it together. So the identity is all the things that are equal. Okay, and negation means I want to look at diverse or distinct elements, right? So I want to look at diverse elements. So all the diverse elements, so all the things that are not equal, are going to be in here. Okay, so that means any two things, so any two, right? Any two different things are going to be related by some positive path, right? So that's all it's saying. It's saying any two are going to be related by some path, right? So that's what I was trying to get at. So identity means they're equal. Complement means not equal. Inclusion means if this happens, then the other thing happens. So if I'm given any two non-equal things, then they must be related by a positive path. Okay, that's all that means. All right, so strongly connected means for any two different nodes, I can find a path from one to the other. Okay, that's all it is. Okay, so let's try reading this one. So let's go for 15 seconds. Try to type in what you can read. So this is an option to try to read these formulae. Okay. So maybe some of you just read it right here, and that's okay too. I'm just trying to give you more opportunities for practice, right? To read these formulae. That's all. Okay. So let's try to see this. Let's try to see this graph. Is this graph right here strongly connected? Is this graph strongly connected? So let's do that. 5, 4, 3, 2, 1. It is not strongly connected. All right, good. 10 people have said no. All right, excellent. So it is not strongly connected because strongly connected says for any 2 points, there's a path. All right, how do I go from 4 to 0? There's no path from 4 to 0. Shucks. 4 and 0 are different, but there's no path. All right, is this graph connected? So the second option, is this graph connected? 5, 4, 3, 2, 1. So who thinks this graph is connected? It is connected, right? Look, they're touching right here, touching. There's no node that's forever alone. There's no node sitting in the corner crying by itself because it has no friends. They're all touching each other, and so every node is reachable by traversing edges in either direction. How do I get from 4 to 0? It's touching 1, and 1 is touching 0, so 4 and 0 are touching, right? Remember, when you say I have a relation E and I put its converse, now I don't care about direction anymore. E union E converse means this is the symmetric closure. This is saying I don't care about direction anymore. Okay, so I'm ignoring direction. So for any two things, ignoring direction, can I get to them? All right, so that's all that's saying. All right, and here I can. So really quickly, who thinks this one is connected? 5, 4, 3, 2, 1. It's connected because there's no node that's forever alone. There's no node that's isolated. So last one. Who thinks this one is connected? 5, 4, 3, 2, 1. The answer is, stay tuned for future. The answer is yes, it's connected because there's no forever alone node. So let's try to make the game a bit more complicated. Let's increase the number of nodes. Okay, so here we have 5 nodes. Let's jump it up a little bit. Ooh. All right, so, ooh, I don't want that. Who thinks, what about this one? Is this one connected? All right, 5, 4, 3, 2, 1. The answer is no, it's not connected because 6 is sitting here by itself, crying in a corner, forever alone, so unloved, no relationships, so sad. So it's not connected. What about this one? Is this one connected? 5, 4, 3, 2, 1. Please do not. Yes, it's connected. Everybody has a friend, either coming or going. What about this one? Is it connected? 5, 4, 3, 2, 1. Think fast. It is not connected because 6, hashtag sad, forever alone, no friends. Very sad. Okay. So I hope this is making you more comfortable doing these graphs. Does anybody want to? So does anybody want to do more? 666 can't be helped. Does anybody want to do a bit more of these? Can somebody like Tammy's remark about why is it always 6? Like that if you want me to do a bit more. Otherwise, we'll move on. Okay. All right, so there's a few people who want to do a few more. So let's do a few more. All right. Maybe you figured out the trick by now of how to find out if they're connected or not. So let's do another one. So is this one connected? 5, 4, 3, 2, 1. What do you think? No, because of 6 again. Hashtag 6. Hashtag 6 life. All right, what about this one? This time you have 3 seconds. 3, 2, 1. Is it connected? No, because of 6 again. 6 is alone. So very alone. So very sad. What about this one? Is this one connected? 5, 4, 3, 2, 1. No, half of 6. All right, 3 is forever alone. So 6 has got friends this time, but not 3. All right, let's change it up. Is this one strongly connected? All right. Yes, 6 found someone. Is this one strongly connected? 5, 4, 3, 2, 1. If it's not connected, it can't be strongly connected. Strongly connected means there's paths in both directions. So clearly not. What about this one? 2, 1. No, because it's not connected. Not connected, so none of these will work. So I hope you played. Let me show you your fantastic prizes. An apple, a water, and me. I'm glad you guys are enjoying this. Hopefully reduce some stress. All right, so let's move on to another cool part. All right. So let's try to read this together. Okay. This part says there is a positive path between 2 nodes. This part says those 2 nodes are the same node. Okay. So there's a positive path, and the positive path starts and ends at the same place. Okay, that's called a cycle, right? If this collection of cycles is empty, then we say there's no cycles. Okay. So, for example, is there a cycle here? Does anybody see the cycle? Let's work it out together. So I can start at 1. I can let me draw it for you so you can see it. Right. From 1 I can go to 3, and then from 3 I can go to 4. Oh, there's no cycle here. My bad. So there's no cycle here because I can't. There's no way to get back to 1. Let's start here. From 1 I can go to 5, and from 5 I can get to 4, and from 4 I can get to 1. All right. So here's a cycle. Notice it starts and ends at 1, right? Or if you think starts and ends at 5, there's a circle here. Okay, a circle or a cycle, whatever you like to think of it. All right. So here's a cycle. Here's another one, right? I walk this way, then I walk that way, and then I walk this way. So that's another cycle. What about here? Is there any cycles here? Let's find out together. So so somebody's asking, what does this mean again? So this means I have a positive path. This means and this means both parts of the path are the same. The identity is x equals x, right? So this is, I have a path, and the start and end of that path are the same, okay? So I've walked in a circle. I walk, but I need it to be in the identity, so the end of my walk has to be back at the start. So I've gone in a circle. I have a circle, okay? Good question. So does a cycle exist if we have a self loop, right? So here we're saying I need to go a positive number. I'm not going zero numbers, I'm going positive, okay? So that's the only thing. I'm going a positive number of steps, right? So for example, here if I start at du and I take no steps, I'm still at du. I need to take at least one step, okay? So for example, here I'm at sq and I take this actual step and I'm back. So here's a cycle, okay? Very boring, but yes, a loop does count as a cycle, okay? When it exists. So here there is no loop, but we can still take 0 steps. There's a path of length 0 here. There's a path of length 1 here. So they're different paths, right? It's like the empty set and the set that contains the empty set. They're very different, right? Okay, dogs. So right here, does anybody see a path? Does this have a cycle? All right. So does anyone see a cycle? Exactly. There is no cycle because all the arrows are going down, 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 down. They all go down. None of them go back up. And a cycle means I have to be able to go back somehow. No cycle, right? Now these really, really interesting, right? This is almost a tree. And so hopefully we'll get to trees in a moment. Let's do maybe one more for cycles and we'll move on. Okay. So I would like to get to trees, but let's do a few more. Just that will be the fun part. It seems somebody muted me. Please don't mute me. So does this one have any cycles? 5, 4, 3, 2, 1. Does this have cycles? Right. It has this cycle right here. Okay. So let's look for interesting cycles that are not loops. Let's look for interesting non-loop cycles. So it has this one, but it has no other interesting ones. Okay. What about this one? Does this one have any cycles? Do you see it? There's an obvious one shouting to be found. All right. So the next step from boring loops, is almost being symmetric. These guys. I have a cycle from 0 and 2. I ping pong between 0 and 2. All right. So very, very lame. Yeah, good job. All right. What about this one? So forget about these boring ones. Can you find any interesting cycles? All right. Do you see any? Up. Does anybody see a nice interesting one? 5, 4, 3, 2, 1. I can start at 0 and walk to 6. And then I can walk to 3. Oh, gotta put that timer off. Walk here, walk there. I can walk here, and then I can walk back up. Okay, so here's a cycle, right? All right. Okay, so maybe let's move on. So there's an interesting thing about these graphs. I took it out from the last one, but when they're connected, and when and of course they're all directed, so we're not working with the symmetric ones, and when they don't have any cycles, then we get a tree, right? We get a tree, and trees are fantastic in computing because trees have this nice property that they're almost like lists. right? They're almost like sequences. But wait, sequences are almost like numbers. So trees are like super fancy numbers. You can think of that, right? So a number is boring. A number is a bunch of sucks, successor, 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 0. A sequence is a bunch of successors that contain information. So they're conses. Here's some info, here's some info, here's some info. Eventually you get to the empty list. So you have a bunch of info and then the empty list. A tree is like a graph, but now you have info and it's not in a line, but it's in a hierarchy. Okay, so the next step up from sequences is trees. And incidentally, trees are graphs. That means lists and sequences are graphs. And natural numbers are graphs. It's all a graph. All right, graphs all the way down. Okay, next. This one has a cycle right here. Somebody was asking, right? I start at 3 and I take a positive step on this one to get to 3. Notice if I start at 0, I have to take 0 steps, no steps, the empty path to stay at 0. But we need to take a positive step. Okay, so that's the difference between this one and that one. Good question. Now ready? So here's what trees will look like if you implement them in some languages. So here's a tree. Let's just focus on this one for a moment. Right. Notice it's connected, right? And of course it's directed. And here's the cool part, right? Every tree has 2 children, at most 2 children. So 7 has this child tree, and it points to this one. We call them children trees. So for example, 2 doesn't point anywhere. 2 is the end of the family line. No kids for 2. But 3 is a parent that has 2 kids. It has a left child named 2 and a right child named 5. Right? So this graph right here, right? Let me time it for you. This graph right here is represented as I have a branch. Okay. Here's the left child. This is the left right here. It's 2 with no kids. Then here's 5 with no kids. And then 3 is their parent right here. Okay. And so this whole box down here is a syntactic representation of this picture right here. Okay. So these trees are specific kinds of graphs, and they can be written inductively. A binary tree having at most 2 kids is either empty, okay, like 0 or the empty list, okay, or it's a branch consisting of 2 trees, some information, right, some information, right, and the other tree. So remember, lists had some information and then only 1 child tree, all right? Numbers didn't have any information. They just had a child tree. That was it. So when we add more children trees, we get interesting stuff, right? So here's Huffman trees, arbitrarily branching trees. These ones are also called rows trees. So in computer science 2GA3 next term, you'll see a lot of different kinds of trees. Trees are easier to work with in programming because of how they can be implemented as inductive data types, right? Notice that here's a data. It's the first part or the second part, right? And they generalize numbers and sequences. So a lot of familiar operations also work here. So we're running out of time. We'll continue with trees next time. Please remember to provide me with a course evaluation online. If it goes well, maybe I'll teach you next term. If you don't think I teach well, then you please make that clear, and then I won't be teaching you next term. And who knows? Anyhow, I wish you all the best, and I'll see you Thursday. I'll be here to answer questions, but everyone else have a fantastic Tuesday. Have a terrific Tuesday.